Good, yeah, thanks for the invitation. I will present the GridTools framework. So this is a set of libraries for weather and climate. But before I go into details, it's not responding. No. And before I go into details, let's talk about why we are doing this and set the frame for this talk. So historically, the weather and climate applications are big monolithic Fortran models. And when you target specific hardware, then you typically tuned this Fortran code to this hardware. And that was more or less doable when there were only different flavors of CPU. And you bought a new system, you would tweak it a bit here and there. But that gets more and more complicated if you target more interesting architectures like GPUs or even fancier stuff. That is probably not even possible directly from Fortran. And we're talking here about codes typically have a size of 250,000 lines of code or more. This is an example here, the Cosmo weather model. The work we are doing is done in a collaboration with several partners. The origin is in about the year 2010, a collaboration between CSCS and MeteoSwiss. CSCS, the Swiss National Supercomputing Center, and is operating the computer for MeteoSwiss, on which MeteoSwiss does the national weather forecast. And at the time, this model, Cosmo, was only capable to run on CPUs, and with what MeteoSwiss planned for the next forecast suite, it was clear that it's not possible to do this with CPUs. So CSCS and MeteoSwiss started thinking about GPUs, which was a rather relatively new topic at the time. And from this collaboration resulted a library called Stella, which you can see as the precursor of the GridTools libraries. There are many other collaborations working on these on the GridTools libraries. There's a strong collaboration with SPCL, the Scalable Parallel Computing Lab at ETH, led by Thorsten Höfler. And there are other partners working on different models, for example, ECMWF, the European Weather Center, which is implementing their finite volume module on top of GridTools libraries. And there's a collaboration with the Allen Institute for AI in the US. They are porting the FV3 weather model, weather and climate model, to our framework, and they did quite substantial contributions in the last 2-3 years. There's another name on the slide, Exclaim, but I will explain that on a later slide. Exclaim and MeteoSwiss, they are targeting the ICON weather and climate model. So what is the GridTools framework about? From my perspective, there are two main goals. First, it should be domain scientist-friendly language or API for weather and climate applications. So domain scientist is the climate weather scientist. And at the same time, it should be HPC, so it should run efficiently on different kind of architectures. The framework contains two main tools, the GridTools C++, which is a direct successor of the Stella that I mentioned previously. It's an embedded domain-specific language in C++. And then GT4Py, the latest development, which is a Python language to achieve the same goal. And there are two flavors of it. And there's some other tools that are not relevant for this presentation. As a warning here, my presentation will contain code. I'm a software engineer, I like code. All the code that you will see is available on this GitHub repository. So let's see how typically model components of weather and climate model are developed. So the domain scientist, the climate scientist will start from some mathematical formulation. I simplified here a lot. This is just the Laplacian applied to some field, not even not even a differential equation. Now, to put this on the computer, you need to discretize it. Here's the 5-point stencil if you do this in 2 dimensions. And then typically as a next step to try your implementation, you will start with a prototype implementation. The modern domain scientist will use Python for this. The older generation probably directly jumps to Fortran. But then if you developed your component, you're a PhD, you're trying a new component, you're developing it in Python, at some point you need to put this into the full model because you need all the other components to play with your new development. That means you need to make you need to put it in the Fortran application, and you need to make it HPC ready because maybe you have to run on big systems for your test case. And that means you're writing something like this. And this is real code taken from a weather model. And what you see here is you want to target CPUs, you write some OpenMP pragmas, you do some explicit blocking by hand, and I omitted some lines here. You put the OpenACC because you want to target GPUs. Then you put this fancy ifdef because on some architectures, one loop order is better than the other. And then finally here somewhere hidden in all this boilerplate code, you will find your stencil. And that has 2 problems. First, you're implementing it 2 times. First in your prototype state, and then in the real model. But also, I don't think writing the model in that way is very attractive. And it's for me very confusing, and I'm super surprised that actually works that well. Now, what we want to change that. And I will use a very simple example to illustrate how these different libraries that I will show how they work. And my example is the following. I apply this Laplacian that you just saw. I apply it twice. So you start from some input field here. You compute to a temporary field and then to your output. And I illustrate this here with a C++ implementation that is representative for what you would see in the Fortran model. I just like C++ better, that's why I use C++. And this is the implementation of the Laplacian. Here's some driver code. And what are the problems here? If you use just a C array here for your memory, you have fixed memory layout. If you do it in Fortran arrays, you have another layout, Fortran layout. And if one layout is better for a given architecture, you have a problem. You should abstract that. There's another problem here, which is the loop structure. Already in this example from the real model, we saw that sometimes it's better to change loop order. There's another thing here, which is explicit loop bounds. So in this example of the Laplacian, you're consuming some halo or boundary lines. So your actually domain where you apply the stencil is smaller than the input array. And if you apply it twice, you have to shrink more. And so you have explicit loop bounds, and that's what you can see in the real models. So this, in my opinion, very difficult to keep track. And still they're doing this by hand. And there's another problem. We're computing here into a temporary, and this temporary is allocated somewhere. And explicitly in this code, we say compute into this temporary. So we have we are accessing memory, and all these codes are memory bandwidth bound. So maybe we actually don't want to write into the temporary. Maybe you want to do compute on the fly and inline this expression into one loop. Now, that you could do by hand. That would be relatively straightforward to do. But once you have done it, you cannot read the code anymore. You don't see that this is 2 times the Laplacian. It's just a very complicated expression. And if at some point you find another architecture where actually this temporary is important or is more performant, then there's basically no way back from this fused code back to this staged execution. Okay, of course, this is very naive code, and you can do much better. For example, you could put your Laplace operator into function, and you call it twice on different domain sizes. And you can do even better with more abstractions. You can remove the loop structure from your concrete stencil implementation, and now you have the freedom to change, actually replace this apply function with, for example, a CUDA kernel call. And if you go on in that direction, you will end up with GridTools C++ or GridTools domain-specific language. And I will not go into very deep details here, but just illustrate the important points where we achieve portability and where our abstractions are. So the first thing here is the storage allocation. We specify here that we want to have a buffer on GPUs, and that will allocate buffer in a way, in a layout that we think is optimal for that architecture. So the library, by using this tag, the library will choose the correct layout for this kind of architecture. There's some setup here on where you want to apply that stencil in your domain. It's not too important. And here's the stencil definition. Now, how do we achieve this dispatching to different architectures? We do this with template metaprogramming. So you basically need to make a lot of your structure of your program available at compile time. You can think of this struct as a function with compile time information. So the parameters of these functions are these accessors, in accessor, out accessor, and to make these parameters accessible, you put them into a type. And there's important information actually here on the in accessor. You describe the extent of your stencil, because that information you can use later. I will show in a minute. Okay, and then the actual stencil goes here, also somewhere hidden in this boilerplate. And it looks quite familiar, but you have to wrap accessors in some kind of context object that will do the mapping to concrete memory locations. Okay, and then there's the next part, which is the part where the stencil, the two stencils are composed into one program. And what do we do here? We declare a temporary here. We don't say how big it is, where it is allocated. We just say we want a temporary with a data type double. And actually, one step more, we say this temporary should be cached, which means, for example, on GPU, you would not actually allocate any memory, any global memory for the temporary. We'll just compute this in shared memory. And then here is the staging of the two Laplacian stencils, one after the other. And finally, we run, and we say this should run on a GPU. And it will all have all it will dispatch to the kernel to have the right memory, loop structure, etc. And now, if you want to switch to a different architecture, what you do is you switch, for example, to CPUI first, one of our CPU backends. And that is GridTools C++, and its library contains some more things for handling Halo updates, for boundary conditions, and more. And this is all available on GitHub. It's a stable release, and you can try it out. And it's actually used. It's used in the Cosmo weather and climate model. Actually, it's used for implementing the performance critical part of that model, the dynamical core. And the dynamical core based on GridTools is officially part of Cosmo release since version 5.7. And the only way to achieve or to get GPU support with this model. And this model with this version is operational at Meteos Viz since 2019. And I will not go into details of these performance numbers, but with this GridTools based version, we are actually faster than with the previous version, with the standard version, which was nice. Okay, what did we achieve here with the C++ libraries? On a positive side, we achieved performance portability. We have a single source code, not big if-defs around platform-specific codes. Single source code, at least single source code on the user side. Of course, in the library, there are different platform-specific parts. And there's a single place to switch the architecture. It's also positive that this is embedded in a language, because all you need is the compiler of that language of C++, the C++ compiler or CUDA compiler if you want to do GPU. And the nice feature here is that you can actually escape the domain-specific language in case your motive is not supported by the language. There is a trivial way how you can still make your code or the part of your application that is not covered by the DSL, how you can make it work. I mean, you will end up maybe with several implementations, one for each target architecture, but at least you can do it easily. Yeah, and we have seen on the previous slide, this library is used for production weather forecast. On the negative side, I already touched on this. There's a lot of boilerplate from embedding in C++. The main part, the stencil itself, was still kind of hidden in a lot of C++ template logic. And if you're familiar with C++ and with templates, you can imagine that compile time of these codes is not super great. And if the user does a mistake, you get nice C++ template error messages that can easily cover your screen and much more. And also there are some limitations that are by this approach, limitations, like if you have specific pragmas that you want to put somewhere for improving your performance, and they need to refer to some variables, that is not possible because the variables are inside the user code and the pragmas should go somewhere into the library code. So there are some limitations by the approach. And what we also don't do in GridTools is this transformation between compute on the fly and the stage execution that I showed. And unfortunately, and probably the strongest negative point is we didn't manage to convince the domain scientists that this is the language to use. So how can we do better? We can switch to a language that is more attractive to the domain scientists. If it's not Fortran, then it's Python. Originally, GT4Py, GridTools for Python, was thought of as just a Python frontend for the GridTools C++ libraries. Now, over the last few years, it developed more and more to a compiler-like toolchain, and that is depicted here. So where you start from is a domain-specific language called GTScript. It's a language with Python syntax, but not with Python semantics. So you cannot execute that language in Python. But we take the AST, we transform it to some intermediate representation, and we apply some transformation. In the end, we code generate, for example, to GridTools C++. But there are other options, like, for example, NumPy, you don't have bad compile times, you get fast feedback, is probably the backend that you want to use for prototyping. We talked also other tools, for example, DACE, which is a compiler for data-centric programming developed by SPCL at ETH. And possibly we could have a backend that targets MLIR, and that is a link to the next talk. Okay, how does GT4Pi look like? And Python is an interactive language, so let's do a bit of interactive supercomputing. I hope that works. So where are we here? This is Jupyter Lab running at CSCS. So I am connected to a compute node of Pitstein, the flagship supercomputer operated by CSCS. And we can use this notebook to execute on the GPUs. So how does our code look like? It's actually here. Straightforward. I think I don't have to say anything. There's the Laplacian implemented as a GTScript function, and then there's a GTScript stencil, which does the staging. So first apply the Laplacian, computing the temporary, apply it on temporary, and write it to the out field. There was a message from Zoom that participants can now see my screen. I hope you could always see my screen. Okay. No, let's execute that code. I will start it here. I chose the backend here already. It's a NumPy backend, and I don't know why, but setting some environment variables here takes quite some time. Should be done in a second. Okay, here we go. Importing some libraries takes also a bit. But the rest is fast. So not super active. Okay, that takes longer than usual. No, yeah, okay, good. So here's some driver code. I prepare some input array, input storage, which looks like this. Prepare some output. I apply the function, and I get this, which is the expected result. I prepared my input such that I expect to get something that's linear in one dimension and constant in the other. And now we can switch backends, switch to the GridTools CPU backend. Let's execute this again. And this, because here actually in this step, by selecting backend, some compilation is taking place in the background. And it was super fast because it was already cached, and I don't dare to rebuild now because it was already not very responsive. And you can execute all this again. You should get the same result, which might be not very convincing, but in the sake of time, I will not change the function here and show you that it actually works. Well, let's look at some generated code. That is the code that got generated now. And what you can see here is GridTools-like code. Somewhere here, we set up this execution. And we see it's only one stage. And what happened here is, if you look into that single stage, is that actually now the compiler was doing inline, something that GridTools C++ alone didn't target. And we can also use the CUDA backend and run something on GPUs. And to see that that happens, I have here the GPU resource available. So you will see at some point, if I execute it, that a GPU was utilized. Here, hardly visible. Okay, let's go back to the presentation. Okay, summary of the Cartesian GT4Pi, of this version of GT4Pi. This is available also on GitHub. It's kind of beta state, and we plan a release in end of this year. On the positive side, I think we improved quite a lot the productivity compared to GridTools C++. It's more concise, easier to read syntax, better error messages. The error messages I didn't show, but you definitely should not get the template error messages from GridTools C++. On the negative side, debuggability is a bit limited because we are generating code. So if you're stepping with the debugger through some code, you're stepping through the generated code, not through the source. And we also have a composability issue that is, in the sake of time, I will not explain what it is about, but basically, if you have multiple stencils, they don't talk to each other. So you cannot optimize across stencils. And then also our languages allows mutable fields, and that requires some complicated restrictions for parallelization. If you look at this simple shifted self-assignment case, then if you want to parallelize that, it's pretty obvious that you should insert a temporary here, which has, of course, performance penalty. So the question is, do you want to forbid such case, or make it obvious that this is not good for performance? So you're not allowed to do this. These are some open questions that we have. And this Cartesian GT4Pi is actually used by the AI2 to implement FV3. And they did some work, and it's better than a Fortran baseline on CPU, the GPU version. Not super great at this point, but they are working on it, and it's getting better. Okay, now our latest development is the declarative GT4Pi. It's a functional stencil language which overcomes some of the issues that I mentioned, the composability issues, removes some weird language limitations that I mentioned. And it has a thin interface layer that allows mutable fields for embedding into existing applications. But it also supports new grids, so unstructured and non-Cartesian meshes. And also we improve on debuggability because we allow embedded execution directly. And it is very early, and I will not go into that code again. This very early work, it's available in the branch currently, but this will be used very soon in this ambitious project, Exclaim projects. I cannot do justice to this project in just 1 minute, so I will not say much about it. There's a link, and you can read about it. It has very ambitious scientific goals, and for us, the important thing is we will port this whole model with a driver and stencils driven by the declarative GT4Pi. And here is my conclusion. So going back to how models are developed, where do we want to go with these libraries? What is our vision? So the domain scientist, the climate scientist, still does the mathematical formulation, discretization, but then he writes architecture, independent declarative code, and then there's a separation of concerns between this part, the domain scientist part, and domain-specific compiler that is written by computer scientists, software engineers, basically hardware experts. But of course, there are challenges in this setup. I mentioned already this trade-off between convenience, like in this self-assignment with shift case. Do you want to allow it or not? It's because it has implication. And there's another challenge here is we want to be domain specific because we know the motives, we know how to optimize them. But of course, there's some model from the domain which has some specific use case, and they say, this is part of the domain. We should incorporate it in our languages. And now you go more and more general, and then it gets more and more difficult to actually optimize because you are going into the direction of a general purpose compiler. Thank you.
Thanks a lot, Hans. I think it was a really nice presentation, and also diving a little bit on the software side, and also I really enjoyed your demo, because it really gave us an insight of your work and your problems that you are trying to solve.